this video will illustrate how we can test our VHDL code using a web-based simulator. So the whole purpose of this test is to generate the timing diagram, and then we'll look at the timing diagram to verify the accuracy of our code. First, we'll log in to make sure that our work can be saved. I will log in with my Gmail account. Now that we're successfully logged in, we will first adjust the settings of the simulator by telling it we want to program using VHDL. Notice how the extension of the file has changed to .vhd. The next thing we will change is the top level entity, or top entity. We'll change it to Testbench because this is our Testbench file name. We'll keep it as it is. Next, we will choose the tool to be the LDIC Riviera 2020. And after that, we will tick the box where it says Open EP Wave after run. This will ensure that the wave form or the timing diagram will appear after we click run. We can save our changes and then start putting our code. I will use the template for the NOT gate and create a new file in here. The Testbench file will contain our code that will test the logic gate code. So the first step I will do is erase everything that I have in the original file. This is a very important step. Next, I will create a new file, name it not_gate.vhd. So it's important that you include the extension as well. Now I will click create file. We will start with the template for the NOT gate. So I will paste the template for the NOT gate and modify it to make it work as any other gate. But since this is the NOT gate code, I will simply save the work. And then I will copy the Testbench for the NOT gate code. We're not gonna explain the details of the Testbench code, but it will basically feed in different values for the input, which is A, starting from 0 and then with 1. And make sure that the Testbench assumes the same name as your code that you're testing. Same entity name, same inputs and outputs as well. Now I will click run to look at the timing diagram. If there's any errors in your code, you will not be able to see the timing diagram. You will see the error messages appearing at the end of the file. Now our input is A. When A is low or 0, the output should be the opposite of that, which is true. That is what's happening. The output is the opposite of the input. When A is low, Y is high. When A is high or have a high edge, when A has a high edge, Y has a low edge. So this verifies the accuracy of our NOT gate code. Now I will close the timing diagram, create a new file, and name it and_gate.vhd. Again, I will use the NOT gate as a template and modify it to make it work as the AND gate. If you want, you can add a comment mentioning your name and a comment saying that this is the AND gate code. First thing we'll have to modify is the name of the entity from NOT to AND. We have to change this 3 times, so anytime, as long as it appears, wherever it appears, we'll replace it with the new name, AND gate. The AND gate that we'll implement has 2 inputs, A and B. So I have to add the additional input B. And the expression, of course, should be A and B. Lowercase or uppercase is the same in VHDL, so I will leave it as that. just quickly review your code and you're done. Now I will copy the test bench for the AND gate. I'll click on copy the AND gate test bench and paste the test bench right here. So I selected everything I had before, Control A from the keyboard, erased it of course, Control V to paste it, or you can right click, choose paste. Now the test bench calls your AND gate code and feeds it different inputs 0, 0, 0, 1, etc. until we reach where both A and B are 1. We will click run to look at our work through the timing diagram. Now I look at A, B, and Y. When A is 0, B is 0, Y, which is A and B, must be 0. This is correct. And since this is the AND gate implementation, I know that the output can only be 1 when all the inputs are 1. That's the only condition for the output to be 1, which is true. The output is high only when both of A and B are high. Here, A is high, but B is low. That's why Y was low. So this is an indication that this is the correct timing diagram for the AND gate implementation. I will close it. Now create a new file, name it or_gate.vhd. Now instead of using the NOT gate as a template, I will use the AND gate because this is the closest to the OR gate implementation. I'll change the comment to OR gate, change the name of the entity 3 times of course, to OR_gate, and here as well, and simply replace the AND operator with the OR operator. Now this is the complete code for the OR gate. We can test it with the test bench code for the OR gate. Select everything in here, remove it, and paste the new test bench code for the OR gate. Notice how I'm pasting the test bench every time in the same file, which is called testbench.vhd, because that's how I named it here in the first place. I will click run. This will open for me the timing diagram of the OR gate. The OR gate outputs 1 when at least one of the inputs is 1. Here B is 1 or high, that's why the output was high. Here A is high, that's why the output is high. Here actually both A and B are high, so the output is high. The only condition for the OR gate to output a 0 is when all the inputs are 0, which is the first case right here. Now the final thing we will do is an expression. I will use the NOT gate as a template, and I will write the expression as a template, as a comment, but we'll start with creating a new file. I will call it exp_behave. You have to spell it this way if you want to use the test bench I provide. Click create file, paste the NOT gate, and as a comment, like I said, I will write the expression that I will implement, which is f is equal to not k and l or not m. So I will change wherever I see NOT gate with exp_behave. You can select this and copy paste it just to avoid any misspelling. Okay, my expression has 3 inputs, k, l, and m. So instead of a, I'm gonna list my new inputs, k, l, m. Y is my output in the NOT gate, but for the expression, the output is actually f. So we're almost done, except I have to replace the expression here with the correct one. So I will translate the Boolean expression into VHDL code. F is assigned a value equals to not k and l or not m. Again, don't forget the semicolon. You can add brackets if you want to make this more readable. So it will be not K and L, or not M. Now we'll test our VHDL code for the expression behavior. So the first thing we'll do is erase the previous test bench, copy the test bench for the expression behavioral code, and paste it here. Now we will run the file and examine the timing diagram. We should have prepared the expected truth table for the expression in order for us to be able to compare it with the timing diagram given here. But if you remember, in the expression we have not K and L or not M. That means whenever M is 0, F must be 1. So this will enable us to test at least half of the truth table. So let's look at the timing diagram and verify that whenever M is low, the output is high. So this is M, and it's low here, the output is high. M is low again here, but the output is high. This is where M is low, the output F is high. M is low again, the output is high. So we only tested half of the truth table, but of course you have to test all the possible cases. So remember that once you finish writing the code, making sure that it doesn't have any errors, compilation errors, the final step is to get the timing diagram to make sure that your code doesn't have any logical errors.